Hello fellow problem solvers. So today we're going to be doing a problem from the USA Team Selection Test 2012, problem number 1. A decent, cool problem, almost a classic in my mind, and a good introductory combinatoric C algebra type of problem that I suggest you try out for a minimum of 30 minutes, ideally an hour-ish, an hour and a half, not more than 2.5, actually not more than 4 hours, given it's a team selection test, and you'd want to see if you could get 7 points on one day at least. So without further ado, let's begin. Now, actually, if you'd like to go along with us, try this out for the next 10 minutes, like see what the problem is asking. And the answer is, well, it's asking, we have some positive integers, we need to figure out all sequences which satisfy this. There's infinitely many of them which are 2k minus 1. And there are no 4 such that this is true. So pause for 5 minutes and ask yourself, what is the sequence that satisfies this? The only one you can think of. And for me, it's, well, ak is 2k minus 1. Because this is even, this is odd, and boom, we're done. So how are we ever going to do this? So like, what's this condition really telling us? Well, it's telling us that from ak, once we get this ak, such that ak is 2k minus 1, all the other numbers, a1 less than a2, less than ak minus 1, less than ak, we have k numbers here. And no two of these sum up to a third. Now we can look at sums on one hand, but what can we also look at on the other hand? Like we know, for example, we know that a1, 2 times a1, isn't any one of these. I mean, 2 times a1 is bigger than this. This is less than a1 plus a2, less than all the way till a1 plus ak. Now, sure, there's k things here, so one of them is going to be greater than, so this is going to be definitely greater than or equal to, okay, 2k minus 1. But if we took this, the one before it as well, say we looked at all of these numbers, we'd have that either like all of them are different, I mean all of them have to be different, but alternatively we could have this one be bigger than ak. And also, on the other hand, if we got a1 to be equal to 1, we would have that these two things need to be distinct. And then maybe from there, we could do a decent job at finishing up our problem, right? We can maybe use some deduction, who knows? So maybe that's a route we can go by, because mind you also, if a1 isn't 1, like here we have, like this is at least 1, and this is equal to ak minus 1. So, but if it's like bigger than 1, then this gives less possibilities down the line if we're looking at it like this. So that's one route to go down, and I invite you to pause for 10 minutes, think if you want to go down this route and go down this route. And the second thing is to say, okay, wait a second, I'm looking at these sums, but the problem with the sums is I don't know if they're bigger, if they're smaller than this, if I'm counting them among the first 2k minus 1 numbers. When I get all the odds, it's not sums repeat, I'm not using, say, 2a2. What is the relationship between 2a2 and a3? I don't know, what do I do? And a different way to look at this is to say ak minus aj equal to ai, right? Instead of looking at sums, look at differences. And we have interesting differences to look at. Which ones? Well, we have ak minus a1 is bigger than ak minus a2, bigger than ak minus 1. Now here we have k minus 1 numbers. We know this is less than ak, which is 2k minus 1. So we know that among these numbers and these, we get all the numbers from 1 till 2k, right? So how can we can we use that in any way, shape, or form? Right, that is the next sort of question. What does this imply also? Does it imply that if A1 wasn't 1, well then that would imply that this is equal to 1. But maybe we can show this can't be equal to 1. Like, what if it's equal to 1? What we have in that case, I invite you here, pause for another 10 to 20 minutes and push the problem further, and now let me clear up the board a bit. And now there are a couple of routes we can go down. One route is to go ahead and say, okay, let's see what happens when A1 isn't equal to 1, and then, well, this is forced to be 1, right? So let's see what happens in that case. Well, then we know we have AK minus 1 is going to equal to 2k minus 2. And we have AK is 2k minus 1. Now, there are different ways we could get both of these numbers, right? Let's see if there's anything to do with that. We have two values. There should be something potentially for us to do here. Now, AK is 1 plus, actually, let's do 1 plus A, actually, let's look at this one first. 1 plus AK minus 3. 2 plus 2k minus 4. All the way till k minus 1 plus k minus 1. Okay, so here we have how many pairs? We have, and we are assuming also A1 isn't going to equal 1 in this case, right? First case, A1 is not 1. We have this. And then from here we have, k minus 1 pairs. And every number is going to be in one of these pairs. And actually, this pair can't happen because if we have k minus 1 is an element, then 2 times that will be equal to this, a contradiction. That's why the evens are good, like if we have an even number, then we cannot have half of it in our set. Mind you, I, j, k don't have to be distinct. So we have k minus 2 pairs actually, because k minus 2 and k, right, this one doesn't work out. So every other number is one of all of these. And if A1 isn't equal to 1, then we know that AK minus 2 is equal to 2k minus 3, right? But then what do we also know then? Well, we know that, you see, 2k minus 3 plus 2 would be equal to AK. So 2 isn't in this. So the next one is equal to 2k minus 4. So this is AK minus 2. This is then AK minus 3. And then just like going down, we'd get AK minus I would be equal to 2k minus I minus 1. And then from here, because 2k minus I minus 1 plus I is equal to 2k minus 1, this implies that I isn't a member, so it means that 2k minus 1 minus I has to be, actually I think I made a mistake, 2k minus 2 here, plus I is 2k minus 2, and so I isn't a member, but then 2k minus 1 minus I is. Actually a mistake again, I should have put minus 1 here, and here I need minus 1, I minus 1, and then we have 2k minus I minus 2. And so we'd have that, all the numbers, and this would go like sort of inductively. We'd then have what? We'd have AK minus k minus 1 to get A1 is going to equal to, by this, 2k minus 1 minus k minus 1, which, when these two cancel out, the minus and 1 cancel out, we get A1 is equal to k. So you get A1 is equal to k, A2 is k plus 1, all the way till AK is 2k minus 1. Right, so let's double check that we have all the numbers here. we have subtract k minus 1 and you get 1 for k. So this is what ends up happening if a1 isn't equal to 1. And now, what do we have from here? We have sort of shown that if a1 isn't 1, when is this true? We've just taken ak, like 1k, that is equal to 2k minus 1. There's definitely many of them. So if we took another one, a1 would still not be equal to 1, and we'd get an a, like for some al, if it was equal to 2l minus 1, if a1 wasn't 1, it wouldn't be 1 again. We'd again get a contradiction. We'd get that a1 in fact needs to be equal to l, a contradiction. And this is, one way of thinking, one way of going about it. And then from here we have that a1 needs to be equal to 1. And now from here we can say, okay, can a2 be equal to 2? And the answer is, well, if it was, we'd have a contradiction because a1 plus a1 is a2. So you would need to have that this number right here is equal to 2 in fact. And so we have so this implies that a1 is equal to 1, and if ak is equal to 2k minus 1, that implies that ak minus 1 is equal to 2, which means that ak minus 1 is equal to what? ak minus 3. And now we can just finish up the problem. Say, take the smallest integer, which isn't equal to 2k minus 1, and then take the smallest next, that's ak, says it's equal to ak minus 1, and then get a contradiction. And that's one totally legit way to just finish up the problem and be done with it. And really, you're just looking at, okay, different ways to look at these sums. Now, another way of going about it is saying, wait a second, I have k minus 1 values which are all distinct from these here. And I'm ordering them, but what am I really using in my ordering? Well, in my ordering here, could have I put another k minus 1 sums that are ordered like this? Like, was there a different way? Could I have put ak minus 1 minus ak minus 2, which mind you is also the smallest sum? Could I have used this in some way, shape, or form to get k minus 1 sums? Differences actually that are like this one smaller than this one, smaller than this one, smaller than so on and so forth. Pause for 5-10 minutes and play with that. Think about that. And the answer is, well, I could have just said, okay, this is less than ak minus 1 minus ak minus 3, and I'll go till ak minus 1 minus a1. Okay, now this gives me 1 through k minus 2 differences, but then I can say, wait, this is less than ak minus a1, and kaboom, I'm done. I again have k minus 1 distinct sums, differences, and that means that these match up. So this one is equal to this one. And as you can see, we can do this for any sort of ai plus 1 minus ai. We can say this is less than ai plus 1 minus ai minus 1, all the way till ai plus 1 minus a1. And then we can go up. ai plus 2 minus a1, all the way till ak minus a1. And here we have 1 through for k through I minus I plus 1. That gives us k minus I differences. And here we have from I to 1 I differences. And a total of, or am I having fun? Like something along those lines. In other words, we get k minus 1 here differences. And that shows that this one is also equal, the smallest one in the set is also equal to this one. And so all these members form an arithmetic sequence. And from there you're done. Like that just means that if some element wasn't, starting from some, wasn't a member of an arithmetic, wasn't in the arithmetic sequence. Actually, how do I put this? If this was, say, broken, the arithmetic sequence rule is broken at some AT, then by taking some n bigger than, some k bigger than t, for which ak is 2k minus 1, we get a contradiction for that t. So this sequence needs to be an arithmetic sequence. However, so if it's an arithmetic sequence, what's its form? Well, its general form is that an is equal to n times the difference plus some constant. Given this needs to be equal to 2 times n minus 1 infinitely often, well, that means that all of these need to cancel out. In other words, d is 2 and c is equal to minus 1. And this finishes up our problem in two different ways. Now, I really like this because, you see, it's a bunch of different, there's two approaches. One is to say, okay, it's either going to be 1 or I don't have a 1. And if I don't have a 1, I'm just looking at these different sums. Mind you, you could have also played around, said, okay, what if a1 is equal to 2? What do I have then? Where's my contradiction? Say if a5 is equal to 9, and that's like my smallest one, is there any contradiction I get with these other numbers? Why can't I fix them in some way, shape, or form, right? You could have played around with that and come up to this same idea. There's different ways to come to the idea. This was one way, just like attacking it directly. I personally feel more comfortable doing this because one, I've prepared for the problem, and two, it's not super duper that level of difficulty where I need to just play around to get comfortable. Whereas here, I am just, let me dive right in. And also, this sort of technique when you're looking at sums, a sort of pigeonhole principle, is if you see it once, twice, 5 times in these sorts of problems, you have distinctness, you're gonna try it out, right? It's going to be one of the first things you try out. And that's literally where this comes from, like trying out a pigeonhole principle in some way, shape, or form. Why is this useful? Then I get 2k minus 1, I get a bound, and then I can just use the second condition, b, to infer these are different from these. And that finishes up our problem. It's pretty cute, in my humble opinion. Let me know if you find a different solution and what you think of the problem in the comments below. And as always, thanks for problem solving.